Phaal, and I'm with InMon Corporation. And I'm going to be talking about the relationship between visibility and control generally, and then more specifically in relation to vSwitch. The first thing I'd like to address is the why rather than the what. And so why measure performance? Most people treat it as an afterthought, and it's added on as one of the last things you do. And I'm trying to make the case that it should be one of the first things you think about, and I want to motivate the reasons why. This slide shows how people typically provision systems today. Typically, you have a workload that you want to stand up, and you don't know precisely how it's going to operate in production. So you make an educated guess, and because it's a guess, and you're a prudent engineer, you build in a safety factor. So you're going to double the capacity of the system that you're going to run it on, and then you think, well, maybe I'll get fired if it fails, but I won't be fired if if I overprovision. So I'll overprovision it a little more. And then over time, the service becomes popular, hopefully. And then you run out of capacity, and you have this failure, and then you run around trying to find more capacity, and then you over-provision again, and then maybe interest in that service declines. And so you end up with all this stranded capacity sitting in your data center. And the reason why you have this problem is really a lack of visibility. I mean, if you had good instrumentation, you wouldn't have this problem. And that's what makes it so insidious, is it's sort of unquantified for most people. They don't realize how much wasted resource is sitting around in their data center. And so really that's what dynamic provisioning gets you. I mean, that's really the promise of cloud computing, is you're creating these elastic pools, and you can right-size them to the actual workload. But to do that, you need good measurements. You need to measure actual demand so that you can provide the correct resources. And then that sort of yellow area is the sort of savings relative to the previous chart. And this is real money if you're in a commercial cloud. These are EC2 instances you're not running. Or if you're the service provider, these are more tenants you can bring into your physical infrastructure and make more money. So when you're doing that kind of dynamic control, you're building a feedback system. And so what you're using is measurements of the system, and you're comparing them to some desired sort of load level. Say I want to run at a loading factor of 0.8 or something. And then your control system is there to add and remove resources as needed in order to hit that target. And when you build a feedback control system, there are a couple of things you have to get right. Some key concepts are these ideas of controllability and observability. And to build a stable feedback system, you need to be able to influence all the important states in the system, and that's the controllability piece. And the dual problem is that you also have to be able to observe all those key states. And you have to have both of those things in order to build a provably stable feedback system. And to sort of use an analogy to sort of bring this home, these concepts aren't all that complicated. If you imagine you're driving your car, you are the controller. And the states involved in describing the motion of the car, its location, speed, direction. And the observability piece is you need a speedometer to tell if you're staying to the speed limit. You need to be able to see through the windscreen. This picture is actually Thule fog in the Central Valley. It kind of illustrates the importance of visibility to the task of driving. And the controllability piece is you need a steering wheel and a brake and an accelerator. And without all of those things, you can't drive. And so that leads on to a second aspect of control systems that I think people are less familiar with. And this is the impact of loop delay on stability. And so this timeline at the top here is basically a control loop that's been unwrapped. So if you think about how a feedback control system works, you start with some kind of disturbance. So in a networking context, maybe somebody launches a DDoS attack against you. It takes you some time to figure out that this is in fact happening, and to characterize the attack, identify which system is being targeted, what the attackers are. And then there's a planning delay as you figure out what to do about it. And then there's a configuration delay as you deploy some corrective action. And then it takes some time for that state change to propagate through routing, perhaps. And then you finally see the effect in that the problem has been corrected. You've dropped the traffic or taken whatever mitigating action you want. And then you observe to see that has in fact happened, and this runs in a continuous loop. The problem is if the time scale of this loop is slower than the thing you want to manage, then you create unstable controls. And so going back to the case of driving the car, if you're slow or distracted or drunk, you weave between lanes, and if you're really slow, you leave the road, and that's an unstable control situation. And so those three things are the things that you really want to look for when you're building control systems: is observability, controllability, and a loop delay that's proportional to the thing that you want to control. So with that context in mind, what is sFlow? The first thing is it's widely deployed. And so if the limit of the span of your control is determined by the number of things you have visibility into, then you want as many things as possible instrumented. And most people's data centers don't consist of a homogeneous environment. There's lots of equipment there, and you need to have visibility into all of it in order to bring them together into one orchestration and feedback system. The other thing is most people are familiar with the fact that sFlow is in network gear, but more recently it's also been added to compute systems, so to report on server and virtual machine and application statistics. And that again is recognizing that your span of control needs to be not just the network, but the physical, the computational resources and the application response time, which is the thing that you're actually wanting to control. So you need to understand the applications and the resources that they depend on in order to deliver application performance. So I don't really expect anybody to look in detail at this next slide. Really what it is it's recognizing that counters are a staple of network system and application performance. And in the networking context, there's the sort of standard mid-2 IF in octets, IF out octets, errors, bytes, and so on. On servers, you have CPU utilization, disk I/O memory, and applications, response times, and various counters. But those counters really don't do you very much good if they're stranded in every switch port, every server, and every application. What you want is an efficient way to collect that data so that it becomes actionable. And really that's what sFlow provides, is just a very simple protocol for anybody who has state to push it to a central analytics system. And so it uses XDR encoding. Each of those blocks of counters on the previous slide is just sent as a densely packed structure. It uses TLV encoding of those structures. It uses a UDP transport. And so the stuff just gets streamed constantly to a collector, which can then build up the analytics for the system that it's being used to manage. Another point to note is that this sort of push model, rather than a polling model, which is often used, works a lot better in cloud environments where you have very dynamic workloads. Virtual machines are being started up and moved and stopped, and it becomes very hard to manage the set of things to poll. Whereas if you have a push model, as soon as a resource comes up, it starts streaming data, you discover it, you continuously monitor it, and so you have good observability. One of the reasons people like counters is that they collapse an enormous state space. So this is just an interface counter trend for a 100 gig link. And what it's doing is it's summarizing an enormous amount of data. There's nearly 1 billion packets summarized per data point on this chart, which is reporting at minute intervals. But when you look at this envelope, it's not really actionable. I mean, you can see that you have a lot of load on that link, but you don't really know what's driving it. So there's nothing much you can do about it. And so you need a way to disaggregate those counters when you decide that there's something that you want to be able to do. And that's the second part of sFlow, is random sampling. So for roughly the cost of maintaining one extra counter, you can randomly sample in this case, the packets traversing the network. in an application layer, you can randomly sample URLs in a load balancer. And then you just stream this data along with the counters to the collector, and that allows it to break out the load. In this case, we can see that it's 3 roughly equal UDP connections that are driving that demand on that link. The other thing for scalability is you want to have very loosely coupled agents on the left of the chart here. But you want a data model that allows this data to be joined at the collector so that you have a comprehensive view of how these resources interrelate and what the dependencies are. And so sFlow uses the fact that it's got instrumentation in the network and it's exporting packet headers to use that as a common key with information it's getting from the servers and applications. So when server statistics are exported, you also export the adapter MAC addresses, which are present in the network traffic. And so you can associate network traffic with hosts. And when you export at layer 7, you export the layer 4 UDP socket that transaction was transported over. And again, that allows you to tie into the network and relate the different services together. And so really the goal is to build the instrumentation that allows you to orchestrate and optimize the software-defined data center. So as I said, everything that you want within your span of control to optimize needs to be visible. And so the idea is to build the instrumentation into all of these elements. So as they get deployed, the system is just automatically instrumented. The instrumentation is built in. It's not something you add on. And by exporting a canonical standard form of measurement, it allows you to sort of break the relationship between having custom agents with custom applications. You have one standard agent, and then you can run as many applications as you like, consuming that data to do different things, and you get consistent results. What's interesting is how Open vSwitch actually drove the evolution of sFlow. Until we started working with Open vSwitch, sFlow really was limited to network gear. It was pretty much in most high-performance data center switches, but nowhere else. But as you extend networking into servers and implement those basic statistics in the Open vSwitch, you recognize that that's not enough to really understand network performance. Because if Open vSwitch is really just an application running on the server, and if the computational resources are constrained, then your network performance isn't any good. And so that actually was the motivation to go to the DevOps community and really sort of think about how do you then scalably manage these computational resources. And so the host sFlow metrics are really the metrics defined by the Ganglia project. I don't know how many people are familiar with that. But it's a project for managing the performance of high-performance computing clusters, and they defined a useful set of metrics that were portable across different platforms. So, they defined them for Linux and for Solaris and Windows. And so the host sFlow project basically leveraged those definitions and said, okay, let's use those, but let's export them efficiently using the sFlow protocol. And then the next thing that happened is we were thinking, well, now that we have this agent that's exporting host metrics, we really need to orchestrate the configuration. So Open vSwitch and the host sFlow agent are sending the data to the same place and using consistent settings. And so the next step was integration in order to propagate configuration data from host sFlow into Open vSwitch, as far as sFlow is concerned. And then the next area was to leverage the work that the libvirt project did in defining sort of a standard set of metrics for virtual machines. And again, rather than polling, which is a very inefficient way to retrieve these metrics, sFlow just pushes them out of the hypervisor. So it scales a lot better than using libvirt as it was intended to be used. Also worked on Hyper-V integration, Docker integration. And then it gets kind of interesting, and I'll have a slide later on talking about sort of convergence in platforms between switches and servers. But the host sFlow agent then was ported to Cumulus Linux and provides visibility into that platform. And then some of the stuff that we've been doing on physical switches has been ported onto OpenVSwitch, so getting information to lags and also integration between sFlow and OpenFlow, so you can tie their two data models together. So if you detect information through sFlow, being able to construct the appropriate OpenFlow rule. So now I'll move on to software-defined networking. And first thing that I think is really kind of interesting is the rise of sort of merchant silicon. And if you look at pretty much anybody's data center switch today, and you look inside, it's very likely to be a Broadcom ASIC. And what that does for you is two things. It gives you standard instrumentation, and sFlow has been supported by Broadcom for a decade now. And the other thing it gives you is a standard forwarding pipeline. Everybody's switch basically has the same hardware, and so you essentially have a very homogeneous environment, which lets you do quite interesting things with performance optimization. And so that's what this next slide is really showing you, is what on the control plane, what this looks like. This is a diagram of the packet forwarding pipeline in a Trident 2 ASIC. And what's interesting is the ACL policy sort of flow table right in the middle there, because it happens as the last thing in the pipeline. So you can sort of have whatever you want setting up your default layer 2 and 3 forwarding tables, BGP, OpenFlow, whatever. And then the ACL table gives you a place to do policy overrides. And what I think is really interesting is sort of hybrid control schemes in which you're using the ACL table to do traffic optimization, and then leveraging the scalability of these larger, more dedicated tables, and the capabilities of mature protocols like BGP to set up your basic layer 3 forwarding. So this slide sort of goes back into the sort of the way we see things converging. I've used Cumulus Linux as an example, but we see this trend more generally that most vendors are using some kind of Linux variant as their operating system on their switches, and increasingly they're exposing the functionality. You have shell access, so maybe you can run Python. You can use Puppet or Chef for orchestration. And I see the trend towards treating the switches as much more open platforms. Some of them even allow you to install your own virtual machines on the physical switches. And so with the host sFlow agent on the switch there, you're getting the standard Linux performance metrics. You're getting the network metrics out of the Broadcom. And then when you look on a server running a hypervisor like KVM with OpenVSwitch, it's a very similar setup. This time you're on an Intel platform, but the hypervisor is reporting the basic Unix stats, and then OVS is giving you exactly the same stats that you would get out of the Broadcom ASIC. And so from a monitoring perspective, you get the same stats end-to-end across this entire system. And that becomes particularly interesting when you look at, say, network virtualization. And here you have, say, a physical server on the left there talking to a physical switch that's doing gateway services. So it's doing the VXLAN NCAP, DCAP, and then the packets traverse across the leaf and spine fabric within UDP tunnels until they hit OpenVSwitch, which decapsulates it and presents it to a virtual machine. And so having this sort of uniform instrumentation across here gives you end-to-end visibility. You can now trace that traffic across both the physical and virtual networks and optimize this whole system. So drilling down further, I think a really interesting property of data center traffic is the observation that large elephant flows actually are responsible for the bulk of the bandwidth consumed. And this is a traffic study from Microsoft, but there are many others that produce pretty similar results. And the basic idea is that most of your flows numerically don't consume much of the bandwidth. They're all sort of control messages, HTTP requests, memcache operations. They're not very large. There's lots of them. They tend to be latency sensitive. And then you have a relatively small number of large flows that represent file transfers, replication operations, and so on, that are responsible for most of the actual bandwidth consumed on the fabric. And this actually is those elephant flows are very amenable to SDN control. They tend to be relatively long-lived in this traffic study with durations ranging between 10 and 100 seconds. And they are 10 seconds or more in duration. And so if you have a control loop that operates in second or sub-second timescales, you can actually affect the outcomes for pretty much all the elephant flows on your network and use that for traffic engineering. And so I think I'll make a sort of minor excursion here. One of the things that always comes up is, what about NetFlow? And really, what I see a good way about thinking about sFlow and NetFlow is that there are two stages in an analytics pipeline. There's always going to be a flow cache. It's just a question of where you put it. If you put it on the switch itself and export expired flows, then really that information is sort of stale and not actionable. Whereas if you externalize the flow cache and you have stateless measurements on the switches and you build your flow cache in software, it gives you really two key benefits that I see. One is that it's software, and so it's programmable and easily tailored to whatever you want to accomplish in your control system. And the other thing is that it gives you very low latency in your measurements. So this is a comparison using OpenVSwitch, which can do both, showing you a large flow as seen by sFlow and NetFlow. And in the top chart, you see that the large flow is tracked continuously over its lifetime. You see when it starts, you see the data transfer rate continuously, and you see when it ends. Whereas with NetFlow, you're seeing records flushed out of the flow cache, so what you get are these punctuated measurements that lag the actual flow and aren't really a particularly good control signal for traffic engineering. So the kind of system we're trying to build here is, as I said, a feedback system, and what sFlow gives you are low measurement delays. SDN automation gives you very low planning delays. It's completely automated. You've taken the human out of the loop. And then OpenFlow gives you a very fast way to deploy control actions. And there are many ways in which sFlow and OpenFlow are really architecturally very similar. I mean, if you look at how you configure them, you're basically just telling the switch where the mothership is. And so you're either connecting it to, on the control plane, you're connecting it to the OpenFlow controller. With sFlow, you're just telling it where to send the measurements. And then all the complexity exists in the controllers and the analytics systems. There's another sort of side diversion here. In operational setups, it's actually very useful to have the host sFlow agent manage the OpenVSwitch configuration. There's a daemon in there that will synchronize the sFlow settings between the host sFlow agent and the kernel data path and other applications that are sitting on the same system. So it provides a very efficient way to distribute state. So this is a sort of case study that VMware and Cumulus put together. And it's showing you that the value of marking elephant flows. So if you put them in different priority queues, you can greatly improve the latency that latency-sensitive transactions see without adversely affecting the throughput of your elephant flows. And what I thought I'd do is look at an example on Mininet. How many people are familiar with Mininet? Do I need to explain what it is? Yeah, basically it's OpenVSwitch with Linux containers on a server, and it allows you to simulate networks. And so this table gives you settings that allow you to scale systems, from realistic production deployments down to Mininet, in order to do tests. And this is an example of marking on a physical switch at 1 gig. And then we're going to build the same kind of thing on Mininet at 10 megabits. There's a utility that we've created that simulates leaf and spine ECMP fabrics on Mininet and connects to the controller. And this is the control script, the entire thing. What it does is you define what your flow definition is going to be, what the flow cache. So you're saying, okay, I'm interested in TCP flows. I want the source and destination addresses and ports. I set a threshold and tell me when I see an elephant. And then whenever I see an elephant flow, I just push an OpenFlow rule out to the edge port to mark that traffic. And so this is an IPERF being used to generate an elephant flow. And you can see you're basically getting the 10 megabit throughput that you'd expect. But this is the effect that it has if you're pinging between two of the VMs. You can see that the response times are severely affected by that elephant flow as it consumes buffers and causes latency. We run a second test running the controller. You can see that there's no difference in the throughput for the IPERF. The OpenFlow rule is pushed out to vSwitch, and the response times are constant. So it's had a great improvement on the latency without adversely affecting throughput. And right now, going back to the physical, at supercomputing, we're running a real-time dashboard. This is actually an example of a bunch of 10 gig elephant flows, running across the show network. And that's the end of the talk. So any questions?
My name is Vinay. I'm with eBay PayPal. So we use quite a bit of vSwitch in our deployments. So one of the issues that we have is measuring flows. There are some flows which get in and consume a lot of bandwidth going through the gateway node, but we need to identify it at the VM level. So I was hoping to hear a little bit more about what kind of integration you've done with the stats on a per flow at vSwitch, and exporting the counters for those using sFlow. So I understand the part about where you replicate the flows and sample, but that doesn't scale for us. So what we would like to do is like every 5 seconds, a minute or so, collect stats for some flows, for all the flows, the top 10 flows, going to each VM on a hypervisor, export those.
But actually, I don't know why you think it won't scale to use the sampling. The sampling rates, if you're using 1 gig network attaches, you'd be sampling 1 in 1,000, which has no measurable impact on the performance of vSwitch. So you can get really good visibility into the flows right down to each VM using the packet sampling mechanism. The other thing that it does do for you is it's exporting the virtual NIC interface counters. And so the vSwitch is essentially polling itself and streaming out all the VNIC counters as well at a configurable polling interval. And so you get both. You get to see the utilization on each NIC, but you also get to see the flows that are driving that utilization.
You're talking about replicating the packet, like at some sample rate to the sFlow collector?
Yes.
So we tried doing that. That doesn't work for us because when you have your 10 gig NICs, you have like 10,000, 15,000, 20,000 VMs. Doesn't scale. So all we're interested in is the counters, not the packets.
But it does scale. I mean, that top of rack switch that all that stuff is going through, it also has or can have sFlow. And it can watch all that traffic.
Yeah,
and those same settings work equally well in the virtual machine.
So in an overlay network, our top of the rack switches, the distribution switches don't participate in this. So we like to put the intelligence in the hypervisors themselves.
Yes.
So maybe we can take it offline.
But for 10 gig NICs, you'd be sampling at 1 in 10,000. It's hard to see how that would have an appreciable effect on the scaling of your the
So
system.
maybe we can talk about it after. I don't want to take up a lot.
Yeah, my name's Andre Fredette from Extreme Networks, and I was curious about how, if there's what kind of research has been done on recognizing the elephant flows. So, if you say, "Well, I've seen a certain number of packets a certain period of time," is that how good of an indication is that this is actually an elephant flow?
It depends. The definition we use for an elephant flow is 10% of the link's bandwidth for a second. So which I think is a very useful definition, because if you think about the resources you have, you don't want to be creating lots and lots of actions. That doesn't scale. So if you're not using 10%, you're probably not worth bothering about. And that works well with, if you think about the resources in a physical switch, the TCAM maybe allows you to do 1,000, 2,000 rules. And say you have a 48-port switch, 480 TCAM entries would allow you to deal with worst case number of elephant flows. And with those settings that I gave, you can reliably detect elephant flows within a second. It's not easy. I mean, that's what we do is the analytics side of it. But it's doable.
So just to clarify, and I think maybe this is what you're saying, but so there's a pretty good, we can all look at the data, the historical data and say, oh yeah, that was an elephant flow. But if you see that happening for 10% of the link for a second, then that's a pretty good indication that's going to keep consuming data for a long enough
it's a
period in the
system.
future.
So if it stops consuming the data, it stops being an elephant, then you'll take away the rule. So it's self-correcting. It doesn't need to be perfect because you use feedback to correct your errors.
All right, we're out of time for questions, so let's thank the speaker.